Hello, viewers. Welcome to my show, Science Thursday. In today's episode, we're going to talk about electrical discharge machining or EDM. So let's get an overview of the whole situation. So what is it? Basically, what is the underlying principle behind it? Well, you have to understand this. Whenever you have electrical short, it can get very hot. Most of you must be familiar with at least one or two burnt electronics, and it can get ludicrously hot, as in as hot as igniting your own home into fire. So it is very powerful, and it causes erosion on your equipment. So that's why you hear in every safety instruction it's like switch off the equipment, then pull out the plug, because if you pull out the plug while it's on load, basically while there is a large amount of current flowing through it will destroy it. Basically that's why if you see any high voltage socket, high voltage I'm saying, basically any heavy current system, they will have like a ceramic backing just to make sure that plasma does not leak and cause damage and all that. So that causes erosion. Now you may think, okay, that must be like a little bit of damage, like, because again your electrical bill is not high enough to so you can melt the basically whole building or something like that. So but you would be wrong in this assumption, because at the beginning of that electrical short, like when that first thing happens, it can get so hot, it's not gonna okay, melt the material or heat the material, it's gonna vaporize it. Basically wherever that first initial contact happened, that matter is gone. Like that physical matter is like, let's say there was copper or tungsten, and it's like gone. Like you literally eroded few milligrams there. Again, not milligrams, nanograms, but you can understand that it can be that power. And if it is done regularly enough, again you can destroy any plug there is. That is why switches are like specifically built to handle that. So that is the core principle. It's like whenever you have this sort of electrical arcing at the beginning, at the very beginning moment, it can get so hot, it's like it's gonna vaporize anything. So we control that behavior. So what we do is basically we have to understand the aspect that maximum erosion happens at the beginning. Like at the beginning, it's like when that first lightning hits the thing, that's the maximum damage. After that, it's just a conductive channel, so it's not going to do much. So you cannot have like, okay, I'm going to turn on the electricity and going to keep keep the electricity flowing. It's not going to do anything. Only at the beginning, when the contact is happening, that's you're getting the maximum damage. So that limits us is that we cannot use continuous current. You cannot simply have a big transformer and give electricity and it's going to do that thing. It's not going to do anything, because that is the whole reason why your switches still remain intact after surviving that kind of damage. It's like once the switch is on, it's not going to do anything. It's like only at the split second at the beginning it suffers the damage. So how do we utilize that principle properly? So first, we instead of using AC, because while AC does allow you to get ludicrously high voltage, inherently by its own nature it's like very limited. It's like, let's say you take 60 hertz frequency, it's like only 60 times a second it's reaching the highest peak or 120 times. So but you can get the point, like the highest peak is not uniform. So we generally take DC. Now you have to understand, DC does give you that oomph, but it does limit the fact that you have to do high frequency switching. Now this is the critical aspect. If without this high frequency you cannot do anything. It's like brushing against two contacts, even as low as 9 volt battery, rub 9 volt battery against each other. It's doing the same thing, it's just not continuous level. Like the frequency is not high enough, so you're not going to do any damage. So high frequency switching, what kind of frequency we are talking about? Like again, you are familiar with 50 hertz or 60 hertz depending on where you live on this planet. Imagine that and multiply that multiple times. So I'm talking kilohertz, as in like 1000 hertz, or as sometimes as high as 10 kilohertz, 10,000 times a second. Basically the electricity is going on and off 10,000 times a second, and generally it's a square wave, we don't want sine wave. So that's what you see whenever you go type in encyclopedia or something like that. You will have a DC system, and then you're gonna have the basically electrodes, basically both of the material acting as an electrode. Your cutting system, your drill bit, quote unquote, and your material which is being cut. So you will have electricity flowing from both of them. Now this thing you can understand, once the electricity is flowing, everything starts to break down. Well, let's say you have two electrodes like this, and you put ludicrously high voltage, as in like as high as 2000 volt or 5000 volt, it will jump. Same way you have a taser, you see that electricity starts to jump from point A to point B. You don't want that. You want it to pile up. Basically you want, instead of shorting at 5000 volt, you want it to pile up to, let's say, as high as 25,000 volt, or as high as you want to. So what we do, generally submerge the whole thing in water. Why? Water is dielectric by nature. It's just because we have so much contamination into it, it's not insulator basically. So we take the water. Now water acts as a good system, not only for helping you basically hold off the electricity. You don't want electricity to jump prematurely. You want it to reach as high power as is there can. The once it reaches that break even point, is gonna destroy that material. Like the short is gonna happen, and that's gonna take little bit material, like milligrams of material. It will short it away, milligrams. But again, you have to understand, it's taking milligram every cycle, and you're gonna have 10,000 cycles a second. So you're gonna do some serious damage. You can cut through very thick material using this system. And water not only is acting as a electricity dam, kind of like where it's holding off the electricity, it's also clearing the materials up. You have to understand, there is no void there. Once that plasma blasting happened, there, all the materials was removed. You have to remove it, otherwise you will you will keep drilling on the same junk. Basically it's the same like when you have electrical drills, and it always have this flutes allows the material to come out. Same is happening there, because there is no actual flute there. So water is acting as a removable thing. It's like it's removing everything. And water must be maintained. Like you cannot just have the water, and you must understand its temperature is electrical conductivity, and you must send it through a pump again. So you can pump everything, and there is also generally ion membrane exchange filters and all that, so we can maintain the conductivity to certain level. Now again, depending on the voltage, sometimes people use oil here in this sort of scenario, but generally water is used. But you have to understand, what is not normal water, is generally distilled water, and maintained at a very specific level. So that's how we can do the cutting. You take a very high voltage, as high voltage as you can get, high voltage DC, submerged everything in dielectric water, and switch on the pulses. Basically tick, 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 you are doing, and it's gonna erode the material level, no matter how thick it is. So why do we want something this complicated like this? This is so more complicated. It's like much complicated than plasma cutter. Why the heck do you want this? Well, first you have to understand, it does not do any damage to the workpiece. If you ask anybody who's dealing with plasma cutters, it's like, hey, can you cut a thin piece of steel? It's like, no, flat out no, because it will warp it just by the heat. Here, nothing, no such thing happens. Like if you want heat sinks, basically very thin materials, thin fins, it can handle it without warping it, doing any damage. So that is very important. Like many materials, many alloys do not like to be damaged. Like even lasers have a limit. So that is the first thing. This will not cause any damage to your material, number one. Second, it's cutting power. Basically, what can it actually do once you have built the machine, once you have all the situation under control? It can cut very deep and very precise. Now deep part, if you are familiar with laser cutter, laser is very awesome. Only problem is that unless you have ludicrously deep pocket, you cannot go into 10 kilowatt laser, and even 10 kilowatt laser output only can cut through 1 to 2 inch thick steel. This puppy has no limitation. Basically, it's only limited by how big the machine you can make. So if you want to cut, let's say, the 3 inch, 5 inch, or a foot, it can handle that. Like it's basically like a CNC machine, only it can cut precisely. It's like, I got this. So that is one of the very core aspect. The cutting depth, it's limited by the machine. There is no physical cutting depth. So even though plasma can cut through, let's say, a foot of steel, it will be like just a slag. It will completely destroy it. And it's very precise, as you can see by this example. Like you cut this basically in a Bridgeport or CNC machine, you will have so much chunk, so much chips flying everywhere, that if you want to recycle that, good luck with that. Like you have to spend so much energy just collecting the chunks and all that. And not to mention, you have to continuously flood the whole damn thing with fluid to cool it, coolant fluid or otherwise if you try to do slim cuts, the heat will warp it. In EDM, you don't have to worry anything about it. Like this whole chunk, like you can fit this chunk back into this, and people will not be able to tell that there are many toys that you can see in YouTube. People are showing like EDM cutting precision. Is like object is like literally once it goes back into the surface is like, dude, where the heck it went? Because it is that precise. And like depth wise, you can have like 1 inch, 3 inch, 10 inch. That's up to you. And it has very low wastage. So let's say you are doing something very extreme, something, let's say, very advanced alloy that is used, let's say, in SpaceX oxygen generator. Again, those materials are very expensive. You want to save every single gram of it. If you use EDM, you cut your part out and then you just recycle the whole thing. Because I told you, like, can you recycle chips and all that? Yes, absolutely. It's a very difficult process. Here, you will just take this pit out, put it back into furnace. So the wastage aspect is also critical, especially if you are dealing with complicated alloys. So what kind of industrial application we are talking about? Like, okay, that's the theory hypothesis. What the heck we actually do with this? Well, first, whenever you're talking about dyes, basically, let's say in plastic molding or some other zinc molding or things of that nature, you need a master die. Now, master dies are generally made with highest quality metal because, again, let's say in plastic, it has to handle high temperature as high as like 500 or 600 degrees Celsius, or sometimes even higher than that. In those sort of scenarios, it has to be like strong enough that at that temperature it does not start to expand or contract. So we use even higher quality material than that. Normal metal, let's say, can only handle 2000 degrees Celsius without becoming warpy. You will put like chromium alloy or things of that nature that will allow it to survive 3000 degrees Celsius. Again, how the heck you gonna machine it? This puppy can handle that without any consideration. It's like even the most complicated hardened alloy that you can make, it will cut through it like it's not even there. So we lot of dyes, like the actual dyes that are used in the industry, let's say Lego dye or things of other that nature, like stamps and all that, those are cut into in their master form generally by EDM. So EDM is the master of the master system. Then this is another aspect. Now again, if you are cutting let's say thick materials, you have only two options basically. Either you use a very high power plasma or very high power water jet. Water jet gives you a very good edge, but again it is also very limited. It's not very precise. This puppy is so precise, so quote unquote clean, that once you have done with the product, you can just push it up like, okay, done. And I mean it. Like, think of this way, this is the jet engine part. Now this is the backbone of why our modern airlines are so profitable. It's simply because this engine, basically this is the turbine aspect. This is what handles the hot exhaust. Now we want that hot part to be as hot as possible. That will increase efficiency. Problem is you're gonna melt it. So what we do is basically have the most complicated alloy we can think of, like titanium, chromium alloy or things of that nature, but we drill holes into this. Now you might be like, why the heck you want to drill hole? That helps it stay cool. So that allows you to increase the combustion chamber, which allows you to increase your fuel mileage. So you can understand, like, you do this in EDM because laser will not do any, like, you cannot do fancy shapes with lasers. On top of that, laser will simply not go through it. Like if you have 2-inch thick material, a laser will simply not do that. Plasma will melt it flat out. No drill bit can be strong enough at that kind of distance, aspect ratio basically. That is why I specified this. Long aspect holes. Basically, if you are familiar with any drill bits, you must be familiar. The slimmer it gets, the more weak it becomes. Like it's like little bit of lateral motion, it will snap. And that happens at 10 to 1 ratio, like 1 millimeter by 10 millimeter depth wise. That is like 10 to 1 ratio. But if here you need 500 to 1, that cannot be done by any other methods other than basically electronic discharge machining and even rocket parts and all that. So it has a lot of application. Basically, it's the master behind the master. So are there any cons of this magical system EDM? Well, absolutely. Well, it has the same limitation as plasma system. It requires electrically conductive material. So if you let's say for some reason made an alloy that is made out of metal but is a very poor conductor, it's not going to cut through it. So that is one major limitation. So you cannot do this, okay, I have a wood shop and I want to save my wastage and all that. It's not going to help you out. So that is one thing. It only works on conductive material. On top of that, the electronics that are needed to do that, super high voltage, super high frequency and all that, those are ludicrously expensive. Not only that, the software needed to drive this and control this is also tedious. Like it's not, if CNC is like, let's say, complexity number 5, this would be complexity number 8, because you also have to maintain the water, you have to maintain the water level, water temperature, water conductivity, you have to maintain all those things. And not to mention the wire that you are using to do the cutting thing, they also erode over time. Because when I'm saying that electrical spark is happening, it's destroying both of them. It's destroying, like, of course you want this your cutting piece to be destroyed, but this tool is also getting, so think of this way, the drill bit is also wearing off. So that is why they require a continuous spool of it. So it has a lot of consumable. Not only you have to maintain the water, which requires you to buy expensive filters and all that, those will erode over time. That is your first consumable. Second, again, water, depending on what kind of energy you are consuming, you may be evaporating a lot of it. The EDM cutting wire itself is very expensive, not something very cheap. And sometimes there are special alloy used into EDM, so most of the damage happens on your cutting piece rather than on wire. So those wires last longer, but again, more expensive. And then not to mention the final electrical load that you have to put into this. So it has a lot of consumable. It's not like put and forget. It does have limitations. Now again, there are a lot of advantage with this, and more people are trying to make this into a final product. Because at the beginning of EDM was like jet engine and all that jazz, but now EDMs are becoming cheap enough that people can build it in their homes. I have provided the video down below. Applied Science guy, again, that guy is crazy. So there are certain limitations. If you want to work with glass, acrylic or things of that nature, only option you have is laser or CNC. So this was my presentation on electronic discharge machining. I hope you liked it, learned from it, or get at least some overview. So what the heck people are talking about when they are talking about EDM. In that scenario, please click the like button. If you didn't like it, didn't enjoy it, I'd urge you to press dislike, press it twice to show me your extra disappointment, and please leave a comment because I reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.